So this morning we're talking about quantum algorithms, and by that I mostly just mean Grover's and Shor's. It's as a quick point of order, there have been some people who've noticed that, like, oh, I'd love it if we went in more depth and stuff like that. But we're accomplishing this over 9 days. I'm trying to keep these sessions relatively short, 20 to 30 minutes, while giving everyone a good base. But I am providing the notebooks, and if you want specific examples or something, please reach out to me. I'd be happy to share that. I have a Grover's algorithm and a Shor's algorithm in today's chat. But that being said, let's go ahead and hop in. So, quantum algorithms. These quantum algorithms have been proposed long before we had quantum computers, where people were understanding that if you had a qubit, if you had a device that could quantumly represent this data, that we could solve these kinds of problems. Today, I'm going to be talking about Grover's algorithm and Shor's algorithm. They're kind of the poster child of the possibilities of quantum. Now, I will say that with this, while we use elements of both Grover's algorithm and Shor's algorithm and many other algorithms, NISQ capabilities, the current quantum computing capabilities, aren't quite to the point for what they were originally designed for. While Grover's algorithm, can search a database much, much faster, the problem is we can't fit a reasonable database on a quantum computer. And then with Shor's algorithm, the problem is noise. That accumulation of noise is that we can't, while it can factor a prime number or a semi-prime number much, much faster than classical computing, for any large number, we just can't maintain coherence on a circuit long enough. However, there are elements of both of these that are being used. So Grover's algorithm is a quantum search of unstructured data. So if you have a list of elements with no ordering to them, they're not sorted, Grover's algorithm is a method to search that data to find the marked item in the database. So you're trying to search an array of n items to find one that's marked. Now, with classical, the big O, the worst case scenario is you have to search through every single item. However, with Grover's has that quadratic speed up. That means that in approximately square root n searches, you can find your items. And this is the showcase of true quantum parallelism, that we're actually searching all the elements at once. That quadratic advantage means that, with 1,000,000 items, you only need to do 1,000 queries. And that square root n makes that advantage so much more apparent as we go to larger items. As I previously said, though, the difficulty is fitting a sufficiently large database onto a quantum circuit. But the use cases that actually exist today is we use Grover-style search for optimization, AI search, and starting to be applied towards seeing if they could more quickly mine like bitcoins and crypto and stuff. The biggest issues, though, is that NISQ noise, this noisy intermediate scale quantum era that we're in, and trying to deal with that. I love this little GIF showing how Grover search works. I'll explain this a little bit more as we go, but mathematically the way it works is we make a guess and we're able to use the oracle to know basically about how far off the guess is from the optimal. We rotate around the searched element by theta elements, then we rotate around the z origin to bring us closer to the ideal solution. Don't worry about that too much, but if you dig into the notebook and are really trying to understand the mathematics behind it, this little GIF here is a great explanation. Three Blue, One Brown also has a great video on Grover's algorithm. I highly recommend that if you're trying to gain the intuition for how the mathematics works. So let's talk a little bit about classical versus quantum search. Classical search does a linear scan. It checks element 0, checks element 1, checks element 2. Okay, in the worst case, you're going to have to check every single element. With the quantum edge, by using superposition, we're able to query all the elements at once. So you'll start in a uniform superposition. That is, all those qubits are set to that equator position with a Hadamard gate where they're equally 0 and 1. And then we're going to amplify the marked item's amplitude iteratively. So what it is we're allowing we have a oracle that's denoting what we want, and we increase the amplitude on the desired state. So there is something to note, though, is that we talk about that square root of n number of iterations. As a matter of fact, your answer gets worse if you go past that square root of n. Since we're rotating around the error from the state that we desire, going past that, you'll start oscillating back and forth. And so it's not only can it find the option in square root of n, but it needs to be roughly pi times the square root of n over 4. You know, so big O square root of n, but the actual time iteration that you should do is pi times the square root of n over 4. You'll notice that's not a whole integer. Generally, we're going to take the floor operation of that. So if we are searching, let's say, 16 elements, all right, we're going to make roughly 3 iterations, because square root of n equals 16 is 4, 4 over 4 is 1, times pi, 3.14, we'll take the floor operation, and we'll do 3 iterations of our Grover's algorithm. There's 2 key components, the oracle and the diffusion operator. All right, the oracle marks the solution that we're looking for. So if we're looking for state W, okay, the oracle will mark that by changing the phase of the element that we're looking for. And the diffusion operator amplifies the marked state, so it inverts it around the mean. And so this little graphic on the left for n equals 100, with that's, you know, so it's searching through this thing. We're starting at, you know, our guess around here, and we are rotating around our error by theta, and then around the origin by the distance to the origin. So it works like by reflecting around these axes. All right, it reflects around the marked state, and then it reflects around the axis to bring it such that the actual state that we want rises to the top, basically. Okay, it starts with all of the states in equal superposition, but as we do that root n number of iterations, it increases the amplitude. So in this little image on the left, we're looking for this middle element here, and as we do these rotations, the amplitude of that middle element increases. Okay, so we're going to build this circuit over here. All right, we have placed the entire state into equal superposition. We're going to use our oracle here to mark the state that we want, and then we're going to apply the diffusion operator. And we'll run this entire circuit, you know, square root of n times. All right, I'm going to talk a little bit about how we do this. So here I've written up some quick code to build a diffusion operator. Okay, we are looking for the state 0, 1, 0, 1. And so to construct my oracle, I'm going to build a circuit that looks like this, and I'll walk through this code with us a little bit. So I'm setting my marked state as 0, 1, 0, 1, and then I'm calling this function that I wrote up to make an oracle. Okay, so I specify that I need as many qubits as the length of my marked state. I initialize a quantum circuit. Then I'm going to iterate through my marked states. A thing that gets a lot of people is that in Qiskit, it uses a little Indian convention. All this means is that the least significant qubit comes first. So if we're looking at our circuit for 0, 1, 0, 1, Qubit 3 is 0, qubit 2 is 1, qubit 1 is 0, qubit 0 is 1. All right? So we're going to iterate through our qubits, and if it's a 0, we're going to flip the state. All right? Using this X. We're then going to apply entanglement between all the states using this multi-controlled Z gate, which is this multi-control, multi-target gate. I specify Z. And then I'm going to apply that same X operation on the other side. Okay? So the effects of this are is that I have marked in the state vector of all these qubits this specific target that I'm looking for, and then I revert the quantum circuit back to its normal state. So that's how you make the Grover oracle. There are variations of the oracle where you can search for multiple targets within, and to do that, you'll just apply your oracle for each target that you're looking for. So if I wanted 0, 1, 1, 1, I would have an X here and no X's on the rest. This is the oracle for the Grover oracle. Okay? Now, I could show you how to build your Grover operator, but Qiskit has this for us. And many of these algorithms are abstracted away like this. That in the Qiskit circuit library, there is a Grover operator function. So instead of me manually building all of the rest of this as my Grover operator, I can simply just call Grover operator. You'll notice that this here is this oracle we just did. So we have an X here, our controlled Z gates, other X's, and then we apply Hadamards, more X gates, controlled X gates, more X gates, more, and there are some great courses on IBM talking about exactly how this works, lots of great YouTube videos. But for the purposes of today, I said, hey, let's just use these functions that are already instantiated for us. So what are some of the challenges with this? Okay, with this Grover operator is the depth. These errors accumulate. For every 2 qubit gate that we apply, we're experiencing 1 to 2% error. So with very wide circuits, we're going to have a large amount of these 2 qubit gates. Mitigation, you can use zero noise extrapolation. That's one of those error correction methods we talked about earlier for amplitude boost. You can use transpolation, just the optimizer, whenever you set up your circuit. Another issue is that too many iterations will overshoot. So you need to do that optimal number of iterations, that pi times square root of n over 4. The extensions, you can have multiply marked ones. You can do amplitude amplification of interesting states. And your Grover operator automatically builds this. Now, this is a quick overview of Grover search, but we do apply Grover search in a variety of different optimization algorithms that we're going to be talking about on Tuesday. So right now, true database search is kind of theoretical. It's just too deep a circuit. However, we do use it with quantum approximate optimization algorithms and with feature search and machine learning. So Grover search already is seeing use cases out in the real world, but the database search still kind of remains beyond what we're capable of. Various estimates between 2030 and 2035 on when that actually comes in. A lot of the crypto people are starting to get concerned about what the applications of Grover search could be on a blockchain. But remember that there's a high oracle cost and that its advantage whenever we go to a structured or sorted data structure kind of evaporates. There are other quantum methods that can help with the structured search. But, with our classical algorithms, we have much better methods for a structured search. All right. Shor's algorithm. Shor's algorithm is generally what people are talking about whenever they're talking about quantum computing breaking cryptography, about quantum computing, being able to quickly crack existing encryption methods. It is a method for factoring large integers. So you are going to factor, p times q primes. Now, classically, this would take exponential time, but the Shor polynomial makes that log of n to the third time. So still a much, much better time. That potentially could break RSA cryptography, the public key security. However, we're already starting to move to quantum safe cryptographic methods. But that's something to keep on the horizon. But Shor's algorithm factors prime numbers. There's more use cases of that other than just breaking cryptography. So the potentials it has for optimization and number theory are huge. The biggest limitation here is that it requires fault-tolerant quantum computation. We don't really have that capability yet. However, underlying Shor's algorithm is period finding. Whenever we say that we are finding a factor of a number, you can graph how frequently that number appears as you're counting up. So you could think of, let's say, you're doing 48, and so 16 is going to appear 3 times as you count towards 48. You could picture that as a wave, and at the core of Shor's algorithm is quantum phase estimation. It uses a Fourier transform. We're able to analyze the composition of different waves that make up a larger wave. And so that has lots of applications for any kind of period finding thing. Now that could be like, your classical physics side of like trying to, do wave decomposition. But also there are all kinds of questions where we're trying to find these periodic functions. That's what a lot of our recurrent neural networks and our time series types of things, where we're trying to find these cyclical patterns in time series data. All right, so classical factoring versus Shor's. All right, with classical factoring, you do a trial division by the square root of n, and the absolute best option we have is the number field sieve. All right, but it's still very secure for large numbers of n. All right, so we're talking about billions of years to break 2048-bit RSA. But Shor greatly reduces this time by this exponential speedup. So with classical, you're checking each period and guessing. Quantum is doing a harmonic analysis on the waves. Don't worry too much here about the math, but at the bottom, so I'm showing this like it's iterating through one at a time, but you have to understand that we're checking all of these at the same time. And so we have these different periods, and what we're doing is checking for when these periods align. And so we will be able to do that in superposition to understand what are the factors of this large number. The basic way it works is that you choose a random number, a less than n, and you find an r where a raised to the r equals 1 mod n. So you place in superposition your entire system, okay, and then you multiply by a modular exponent. All right, then you apply this quantum Fourier transform, okay, this way of decomposing a set of waves into pure sine waves. All right, and then you measured your continued fractions to get your r. All right, so this oracle provides this modular exponentiation, which is really efficient on quantum computers. All right, so you initialize your register, you place in superposition, you exponentiate, you pass it through your quantum Fourier transform, you measure, and you classically post-process. Okay, so your interference will peak, like your wave function, at periods of 1 over r, these factors of this integer that you're looking for. This quantum Fourier transform is at the core of Shor, okay? It does this modular exponentiation, but it's largely based just on Hadamard gates and controlled phase gates. But it still has that n squared number of gates. where n is the number of qubits. So that's one of the reasons that it's still so costly to run Shor. But as we approach fault tolerance, that place where the number of logical qubits we have becomes more and more useful, we're going to greatly see that Shor and the underlying quantum Fourier transform is going to have great possibilities for any kind of time series or series type data like this, where we're looking for these cyclical patterns, these sine wave type patterns. These NIST challenges, all right, that deep depth there is a real challenge for the errors that accumulate. Okay, this little 5 qubit example down here that I put, this is what your circuit looks like just even before you do the quantum Fourier transform. So this is just setting up your state and doing the modular exponentiation, even before you get into the quantum Fourier transform. So you end up with very deep circuits very quickly. So even for relatively small period finding problems like this, we require some form of error correction. So we're going to need real fault tolerance before Shor breaks encryption. Yeah. Implications, the crypto revolution, RSA and ECC are vulnerable post-Shor. We need post-quantum encryption methods. NIST is already moving towards this. There are classical encryption methods that are safe to known quantum algorithms at the moment. And so, we're already moving in that direction. The biggest threat is largely from harvest now, decrypt later schemes. But even another point that I like to make to people is that, with classical algorithm, breaking RSA 2048 encryption takes 10 to the 20 years. Okay? Now, we can get huge speed ups with quantum, but it's still going to be a very expensive, time-intensive operation to factor these large numbers. Hey, we are, far and away quadratically faster than that, but we're still talking about maybe, weeks or months of computation to break a key. So I don't think that's something that most people would need to worry about. Perhaps like governments or multinational corporations are super concerned about having their things broken. But that's not to say that Shor's not useful. This period finding and this ability to factor these large numbers is going to have large implications for other domains, but I don't believe that breaking encryption as it exists now is the major impediment. All right. So for anyone who joined after I started talking, this is a brief overview of what Shor's algorithm and Grover's algorithm are. I've included a couple of notebooks in the chat under quantum algorithms that we are able to, that gives you the detailed, line by line breakdown. And if you're really wanting to understand these algorithms, you're going to have to start pouring into the math and things like that. But these are the foundational algorithms for quantum computing. These are kind of the poster children that were developed to, and they kind of serve two purposes now. One is that as the technology advances, we're moving towards a state where these become more and more useful. They're starting to see use cases outside of their original intention. So we're using Grover's algorithm to, optimize machine learning, even though we're not using it for large database search. We're using aspects of Shor's algorithm for number field theory and trying to find patterns in time series data. But they're a good way to kind of break in and start understanding how we encode data into a quantum circuit, how we measure things. The phase kickback mechanism in Grover search is interesting, but it takes a little time to wrap your mind around. We will be moving on later this week to the variational algorithms, and they employ a lot of these same techniques. So, does anybody have any questions? What are the other domains I might think are affected? So the way I see quantum, it's going to have certain niche use cases where it breaks through first. Okay, right now, quantum chemistry and finance seem to be the vanguard of what's gaining traction on using quantum. And there's a real aspect here as well where we're very used to very mature algorithms in the classical space. Even the machine learning algorithms we use are largely variations on things that have existed for 30, 40 years. Back propagation being applied, is the biggest, advent. But like these are variations on this. But also, we're still developing and discovering algorithms. Sample-based quantum diagonalization came out early 2025. So it's one of those things where it's difficult to tell what's going to be the primary applications of quantum computing because people are still developing the algorithms. Go out there and see if you can come up with a way to solve a problem using quantum. But it's still a very young science, and we're not just developing the hardware, developing the software and the algorithms on how to use this quantum hardware. Yeah, and so as far as domains, now we can take a little bit of guidance from what quantum does. The superposition aspect, we're always going to be looking for domains where we're fighting some type of combinatorial explosion where classical computing can't do it. In the early days, I talked about how there are some problem spaces that have a larger solution space than there are atoms in the universe. And so whenever we take a look at those kinds of problems, the answer isn't a bigger supercomputer. We'll never be able to solve the problems like that, where the number of possibilities just outstrips our ability to compute them. So it's going to be these high combinatorial optimization spaces where we're looking for quantum to give us an edge. In other domains, you could put it on a quantum computer, but most likely classical computing will be able to do it. If it's largely a linear processing problem, it doesn't make sense to use quantum computing for it. The 2030 time on the estimated date, so that's a rough guess based on the current growth and things on whenever we might be able to start using Shor's algorithm to break RSA length chains. Okay, RSA 2048, this is just like the date when we have a quantum computer big enough and that can potentially have enough coherence to solve that kind of problem. Think of that as rough, call it 5 to 10 years in the future. But NIST is the something international standards, something like that. But the people who recommend which encryption methods and stuff to use, they've been moving past RSA encryption for a long time. People have seen the writing on the wall on this for a long time, and they're like, hey, there's other methods that aren't as easy for quantum to break. We're going to start moving in that direction. So that's why I don't know if they have a deadline per se, but I know they've already been moving that way for a long way. Are there any other questions? All right, everyone. Thank you so much for coming out this morning. I do have the video attestation up on quantum algorithms. Please take a moment to fill that out. We'll be back at 2 o'clock to talk about optimization and hardware challenges, about the difficulties of deploying to the actual hardware and how to make your circuit as efficient as possible. And then tomorrow morning, on Monday, we will be talking about the hackathon for the people who are trying to get a project ready for that. I'll be giving some tips and tricks on how to have a good hackathon entry. I've done fairly well in years past, so I think I have some insight on how to make the best poster, how to have your elevator pitch, how to make a good video. And then our guest speaker at noon on Monday. Please tell your friends. I'll add anybody to the Discord who wants to watch. But I'm really excited that someone from IBM is taking the time to come talk to us. So please, 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 if you can, show up for that. All right, guys. I'll see everyone at 2.